Hello everybody. I want to go over some regression analysis, simple little regression analysis in R. I'll probably do this over a series of videos, and this is just the first crack at it. And I want to begin by actually creating a data set. I find this to be a very useful way of understanding what's going on. What we do is we create a data set and then see if we can predict our expected effects or terms in this data set. We'll start here with two independent variables. These are the variables that measure something that we're interested in and that we think are going to have some sort of predictive power over another variable. So I've created two here, parent income and education. And I'll just jump here to the fourth variable, which is income. So the idea is, let's just imagine we're doing a survey to understand what predicts a person's income, and we reduce it to two main effects. Fixed effects, parent income and education. So basically that's the structure of the model. And then I also add some error. So this error is basically all the other stuff that we're not explaining in the model that could explain income. So these are things I'm making. I'm making the data. In the real world, you never do this, of course, but we're doing it here for information purposes. And once I've created those data, I create this dependent variable. This is the variable that we're trying to predict. And I've added these terms here that we're going to actually try to estimate. This is going to be the constant that we're going to try to predict. You might call this the intercept or the constant. This here is the term for parent income, and this here is the term for education. So these are the coefficients that in this made-up data are going to be basically, you can think of them as weights associated with each one of these terms, parent income and education. And normally you don't actually compare the magnitudes of these things because you can't directly compare them usually. But just for the sake of example, let's assume that these are directly comparable variables. We might say that because this coefficient's larger, it's more important than this coefficient. But I would stress that in the real world, you can pretty well never do that. I would never want a person to try to interpret the coefficients based on their actual magnitude or size. Okay, so I've created the data. Now I'm going to combine these data into a data frame like this. Once I've created these data, I'll put them into a data frame. In this case, I just bind them together, and then I use this as data frame function to create the data frame. And now I've got these data all together. I can take a look at them here. You'll see that we've got the income variable, the variable we're trying to predict, and these two other variables, the education and parent income, we're using to try to predict income. So now I'm actually going to run the model. And the results here in the console, which you can barely see, here, these results in the console are basically the predictions of this model. So if we didn't do this, and we had the data, but we didn't actually create it, these terms here are the model's attempt to estimate these terms here. So we got -1, 0.2, 0.75, and we've got these data, and we're trying to estimate it using this linear regression model, and we estimate that the constant is -1.4360, and the coefficient for parent income is 0.2, and the coefficient for education is 0.9. And they're all kind of close. They're not exactly right. You can see 0.9 is close to 0.75, 0.2058 is very close to 0.2, and then this is fairly close too. So we'd never be able to validate it, but this in some sense is an empirical and very unsophisticated way of validating the whole process of linear regression, because we can see that the predictors are fairly close. In fact, they're the best you can probably get, as it turns out, in this simple case. But we want to do more than this. We don't want to just be looking at only these coefficients. And so if you can create this object class associated with the LM function, this linear model function, by doing this, and it creates an object class out. And then with that, you can do all sorts of things. So by using the summary function, we can get a more complete output of this model, including, again, the same coefficients, but in addition to that, some other information. One of the key things that people like looking at when they're using linear regression is to look at the adjusted R squared, which is down here. This is basically a way of explaining, or it tells us about the proportion of the dependent variable that's explained by this model. Explained, I would put into quotes, but basically it's the amount of variability that the model, in quotes, explains. And then we can also do the standard diagnostic, which is, there's actually a lot of these little things you do if you're doing a comprehensive regression analysis, which I'll look at in future videos. But one of the things you might do is actually plot out the residuals. These plots, typically what we're looking for is some symmetry for the residuals. Ideally, no pattern about the center. So typically we would like there to be kind of a mirror image, very roughly, about the 0 here, so that the residuals are kind of randomly distributed. And they roughly look randomly distributed. They should be actually about this axis. It doesn't matter as much if they were randomly distributed across the x-axis in this particular graph. It doesn't matter as much. What matters is that they're randomly distributed across this axis, so that this side and this side are kind of roughly a mirror image of each other. Now, that's all well and good. I've got some basic regression analysis, and you've seen how it can be done. And if you're looking at this video and you've never seen that before, that's helpful, presumably. But I want to look at a scenario in which we actually drop a variable. So we're going to introduce what's called an omitted variable bias. So what I'll do is, the step 1 is to run the model again, but this time only with parent income. So we're forgetting the complete model. We've dropped it. Now in this case, if you actually look at the prediction, believe it or not, this parent income, if I just drop the education variable, this remaining variable that I'm predicting is actually not biased, not in any systematic way. The prediction itself might change a little bit. The coefficient that's predicted from this model might change a little bit, but the truth is we know that it's not biased, provided that there's no correlation between the independent variables, the missing variable and the variable that you have in your model. And in this case, we know there's no correlation because we created the data without a correlation. So what this basically tells us is that if you forget to include a variable in a regression model that you should have included, however, that variable isn't correlated with any of the other variables in the model, then as it turns out, it doesn't matter that much. It will reduce the predictive value of your model as a whole. Your R-squared will almost certainly go down, but the coefficient itself won't be biased. It might change, especially if the data set's small. It might change, but it's not biased, which means it's not going to give you a systematically wrong answer. You can have some confidence in that. However, there are circumstances in which that's not the case, in which a missing variable can result in a biased result. It can result in a bias. So I'm going to create another data set here. In this case, I'm going to introduce a correlation between the two independent variables, parent income and education. So I'll do it like this. So I'm creating these two variables, but this variable is a combination of this variable and the random number generator. So that imputes a correlation between these two variables. Then everything else I've done is the same. Okay, so I create some data. I create the data frame. I do the regression analysis, and I look at the output. So these are the coefficients for the model I just estimated that doesn't have an omitted variable. So the variables are correlated, but they're both included in the model. Now, just to illustrate what's going on here, the final step, I will drop now the education variable. So now education and parent income are correlated with each other. I will run this regression model and look at the outputs here. And I would point out that this parent income variable, parent income was, when I ran it originally, it was negative 0.2396. When I ran it after excluding the education variable, it changed quite a bit. And this change actually represents a bias. Because what actually happens is that this parent income variable, it's explaining variation in the dependent variable accounted for by itself, but also by the missing variable. Which means when you have an omitted variable bias, the coefficients associated with the variables included in the model aren't reliable. It can't be reliably interpreted. And in some cases, they'll be systematically biased upwards, and in some cases, systematically biased downwards. So And unfortunately, there's not a real way data analysis can solve this problem. So it's an example of a problem that we probably see a lot in some fields. Certainly in the social sciences, you see the potential for this a lot, but there isn't any way to know ahead of time. So there's no way to use data to identify or solve this problem. It's just kind of there. And you need to use your expertise and your knowledge of the field and so on to select a proper model. By and large, that's the only thing you can do. You can't solve an omitted variable bias statistically. It's just a problem. There might be some ways to help solve it, but by and large, it's the kind of thing that just requires better science, a more rigorous data collection, and so on. So that's just a background, a really quick overview of regression, and including one specific problem related to regression. That's the omitted variable bias. And in future videos, we'll dig into some other issues to think about and more complex models. Thanks.